So this section is about quantum numbers in electron configuration, and it's really an extension of the quantum numbers section. So before you look at this section, you should go read the quantum numbers page. So quantum numbers' main purpose is to explain where any electron is positioned in an atom, and moreover, when you look at all of the quantum number sets in an atom, you're able to get a look into the atom's electron configuration. So the principal quantum number dictates the electron shell that you're in for a particular electron. Then the angular quantum number specifies the subshell of you're in for that particular shell, and to the right is a picture of the possible orbitals for the first three shells. Then the magnetic quantum number describes which orbital you are in your particular shell. So it breaks it up even further and adds a third dimension. And as you can see in the image, some subshells have different possible orbitals that all have the same energy, and that's why they end up in the same subshell. So you see each subshell represents an energy level in the shell, and then there are multiple ways of representing that energy, and that's where the different orbitals inside the subshells arise. Now, the magnetic quantum number is especially important because it explains why a subshell like P can contain 6 electrons in total when every electron cloud, or orbital, can only hold 2 electrons. And it's because the magnetic quantum number allows for multiple clouds to exist in the same subshell. And the final quantum number is the easiest, again, as I said in the quantum numbers page, is the spin quantum number, which allows for every electron cloud to contain 2 electrons and yet still maintain adherence to the Pauli principle, which I talked about also in the quantum numbers section. The spin quantum number is either 1/2 or -1/2, denoting clockwise or counterclockwise. Okay, although the angular momentum itself can have any integral value, that doesn't actually necessarily mean that you can have an infinite number of subshells to every shell, that it can just keep going on, because certain values for quantum numbers begin to contradict other quantum numbers and other laws in physics, and sometimes they don't contradict rules, but instead they're just theoretical. We haven't been able to synthesize atoms that make use of these subshells. So there's a useful chart towards the middle of the page that kind of explains that. It shows you how, as you move through the periodic table, you move diagonally across subshells, as so, until you get up to 8s, and that's where things start getting theoretical. And then there is a diagonal-ish formation that you can see, and anything in the upper right-hand corner of that, those are all contradictory and therefore unallowed quantum numbers. So the same is also true for the n quantum number, because anything over n equals 7 is purely theoretical. So overall, quantum numbers determine the location of the probability cloud that an electron inhabits, and how different clouds are positioned in relation to one another to describe their electron locations on a whole. And that's just about it for quantum numbers and electron configuration.